A list of what Power Pmac does. Note that Power Pmac is a computer. We talked about that earlier. Power Pmac is a Linux computer. And so Power Pmac executes the synchronous sequenced motion programs, script motion programs. It executes the real-time asynchronous PLC programs, script and C. Remember, Power Pmac is both a script and a C motion controller. Power Pmac performs the kinematic transformations, computes the commanded motor trajectories, processes feedback and master position data, and there is a special feature that Power Pmac has for processing the feedback. We'll talk about that a little bit later on. Power Pmac closes the position and velocity loops of all of the motors that it's currently in control of. It also calculates any compensation table corrections. Provides the ability to synchronously gather data of any desired register. Anything that is a memory register in Power Pmac, which everything is, can be gathered at either the phase or the servo rate. Performs the electronic phase commutation, another very important feature of Power Pmac. Also could close the current loop. So not only could Power Pmac close the servo loops, close the commutation, it also can close the current loops between the drive and the motor. Very important feature. We'll talk more about that a bit later on when we get into some of the details of the motor setup. Power Pmac is also performing a number of safety checks at various points in its priority level. And then it's responding to any commands from the host computer, what we call online commands. And then, because it's a Linux computer, it can also execute the independent C applications, things that would run entirely in C, just as any Linux computer would do so. So the task priorities in Power Pmac. The highest task that Power Pmac has is what we call the position compare ISR, interrupt service routine. This is where the hardware feature of Power Pmac, the gate array, and I'll talk about the ASICs a little bit later on this morning, probably into the afternoon after lunch, and then we'll get into the motor, the actual hardware features that the motors offer us. And so this ASIC has the ability to do what we call capture position data based on a trigger, or based on a position value in a register, it will then do a compare, and it will fire an output. So it'll fire a digital output based on position values in a register or a series of registers. And this is a hardware feature of the ASIC, so it's extremely fast. It's in very, very, actually it's in picoseconds. It happens on the order of picoseconds, this process. And there's an interrupt that can be generated within Power Pmac so that you could drive external activities in a C routine. We'll talk a little bit about that later. It's a very, very high priority. It could be as high as 80 kilohertz or higher. The phase interrupt. This is the frequency set by the servo or the macro IC for doing the motor phase commutation, motor current loop closure, and any data gathering at the phase rate. Power Pmac can not only gather at the servo rate, but at the phase rate. All right, so you're going to see a number of similarities, and you're going to see extended benefits that you get from Power Pmac compared to Turbo Pmac. The servo interrupt frequency, that is the next priority in Power Pmac. This is where encoder conversion table processing occurs. Trajectory update calculations happen in a part of the servo update that happens right after the servo update. The fine interpolation is directly in the servo update. Compensation table calculations happen at the servo update. Position and velocity loop closure. High priority safety and status checks, because some status checks can be done in the background, some can be done at a higher priority, and these would be done at the servo interrupt. And then servo data gathering. So the typical data gathering most people would use at the servo update. After the servo update, there's another priority called the real-time interrupt, and this is generated based on the servo frequency. and then so many number of servo cycles. Every so many number of servo cycles, we get what's called a real-time interrupt. This is where the actual motion program calculations are done. All the segmentation, course interpolation, kinematics, and look ahead. So the basic trajectory generation from the motion program. Foreground script PLC PLC program calculations occur here. We have background PLCs and foreground PLCs. The foreground C PLC programs, because there's both background and foreground C PLCs. And then the medium priority safety and status checks. And as we get into the actual registers that Power Pmac uses to control these items, we'll talk about them in more detail. Last but not least is the background tasks, where a number of things happen. This is where Power Pmac schedules all of the background script PLCs. They execute one script PLC at a time, and then one scan of all the active background C PLCs. They all run together as a contiguous group. Then there's a status and housekeeping that occurs. This is where Pmac periodically checks its memory location, also checks all of the safety features. For example, when it's looking for over travel limits, it's looking for certain types of current limits, certain types of position limits. These are all checked in the background. And then the background releases to the Linux operating system, and this is where the Linux tasks will then take into place. So any of the independent C applications, this is something that's just running in the Linux operating system, and then the Linux operating system tasks. The time that's allocated between these various tasks and the operating system tasks is called a sleep period. We'll talk about this in a little bit more detail when we get into the C programming. And so there is a structure name called sys.bg sleep time. And this is set in microseconds. So if we take a look here at an example timeline that Pmac has, we can see here's the phase interrupt. And notice how interrupts are phases in red. So here's servo interrupt now. And you can see every so often the phase is interrupting the servo. Here is the real-time interrupt sequence. And now we can see that there's a phase interrupt, there is a servo interrupt, and then the RTI happens after so many servo cycles occur. And then if we take a look at background cycle, we can see that's constantly being interrupted by the phase, then the servo RTI. So basically this prioritization of Pmac is what allows it in any given amount of time, and this would just be real time. So we're looking here at real time in Pmac. If we were just to piece it up and just take a look at the phase all by itself, or the servo all by itself, or the RTI all by itself, we can see that Pmac is putting together all of these different priorities so that it can complete all the tasks it needs to do in a given amount of time.